Hi. So we are continuing in chapter 4, lesson 2. Okay, 4.2. In the previous video, we discussed special types of rational functions, which are the reciprocal functions, right? 1 over x and 1 over x squared. And we looked at their transformations, right? And if it is ax plus b divided by cx plus d type, then we learned that we can use synthetic division and convert it into a rational function, which is a reciprocal function. Basically, reciprocal means the numerator is a constant. Okay. Now, sometimes you can have more general rational functions, right? The numerator is also not a constant. Now, in this lesson, we are discussing that. Okay. And in that also, we are starting with the simple type where the numerator and denominator have no factor common other than 1. Okay. So, in that case, what happens? Because there are no common factors, okay, the idea is simple that both numerator and denominator will have different sets of zeros, right? If they have the common factor, it will have the same zero. Otherwise, they will have different sets of zeros. So where the numerator becomes 0, the whole function becomes 0. That is the y value. The y equals p of x over q of x, right? If the numerator p of x is 0, then y is equal to 0. And as a result, you get x-intercept. It has to be on the x-axis because the y value is 0. And similarly, to get the y-intercept, by the way, right? This is your graph. Let's say, it intersects here and again here. So that doesn't look like a function. Let me redo it. Again here, let's say. Then you have those two x-intercepts there. But where does it intersect on the y-axis? That point there is your y-intercept. And that is where your x is equal to 0. So you plug in x equal to 0. Okay, the value is not 0. X is substituted as 0. Then whatever the p of x over q of x becomes when you plug in 0 for x will be your y-intercept. Okay, that's easy. You don't have to solve any equation. Just plug in 0 for x. You get y-intercept. Similarly, now while if I have to sketch the graph of a function, I need to know where the asymptotes are, right? And you take the denominator and set it to 0, you will get the vertical asymptotes. Okay. The horizontal asymptote is a little different. Okay. Now the horizontal asymptote comes when you go to either plus infinity or minus infinity, right? On the two extremes. We cannot plug in infinity, but we can have an intuitive idea whether the asymptote will exist or not. Okay. How? Suppose here, okay, regarding horizontal asymptote, suppose your rational function is like that, x divided by x square plus 1. So the degree of the numerator, x is 1. The degree of the denominator, x square plus 1 is 2. The denominator has a higher degree, then that will become that will become large much faster than the numerator. As a result, the ratio will go to 0 and you get your horizontal asymptote y equals 0. We read this as low divided by high. Okay. Low means the exponent or the degree of the numerator is low, compared to the denominator. If it is the other way around, okay, if your numerator has degree 4 and the denominator has degree 3, you have to look at the highest exponent in both numerator and denominator. Okay. So it is high over low situation. then the numerator is going to infinity faster than the denominator. As a result, your values will go to infinity on the two sides. It could go to plus infinity or minus infinity, we don't know, but eventually they'll go to infinity on both the sides because the numerator will dominate. Okay. And as a result, you don't get any asymptote. And so low divided by high, high divided by low. What if both are equal? That is same divided by same. Okay. So an example here you can see 2x square divided by this expression which has 3x square. I have highlighted in pink the terms that determine the degree of that polynomial. Okay. So it's not always the first term, it could be any term in that expression where the exponent of x is largest, right? Now in this case, x square is the largest exponent in numerator and denominator. And then what happens? In the long term, when you take large values of x, only x square matters. Okay, the minus 2x or the minus 4x in the denominator, those values become negligible. Okay, and I'm going to write that now here because I have talked about this concept a number of times, I guess. I have not written explicitly. Okay, so let me write it. Becomes negligible for large x. The same with the denominator. Okay, and all the lower degree terms. That means essentially you only have to focus on the highest degree terms. That means if you look at this expression, in the long term, this will almost be like 2x square divided by 3x square. The rest of them are like negligible. Okay, and as you can see, now you can cancel the x square and get 2 divided by 3. Okay, and let me mention that here. As x goes to infinity. As x goes to infinity, the values become only the highest degree terms. Okay. And your asymptote, now you look at this equation here, then it will make sense. Y equals the lead coefficient of the numerator divided by the lead coefficient of the denominator. So in this case, y equals 2 over 3. That will be your asymptote. Okay. All right. So some notes here, a function can intersect a horizontal asymptote. That is, what it means is, I'll draw a graph to illustrate that. So when you say horizontal asymptote, normally when you say asymptote, we don't touch that asymptote, right? We get closer and closer to it. But in the case of horizontal asymptote, what you have to understand is, suppose this is your horizontal asymptote. Okay. And it can happen that your graph, let's say, I'm just drawing one situation, could be like this. No. So it eventually becomes closer to that. So that is your asymptote. But before it became an asymptote, for some finite values, the graph could have intersected, right? So that's what we mean by the first statement here. A function can intersect the horizontal asymptote. Now that doesn't happen with vertical asymptote, you have to understand, okay? Because if there is a vertical asymptote, the values of the function are going to infinity, so it cannot be on that line anyway. But it can happen with horizontal asymptotes like this. And you can have at most 2 horizontal asymptotes. One on the right side, one on the left side. Now, not necessary, by the way. Sometimes you may not have asymptotes on 2 sides, or you might have the same asymptotes on 2 sides, like all the previous functions we have studied, like 1 over x, both on the left and the right, they become closer to the x-axis, one from above, one from below, but the same line, right? Sometimes you might become asymptotic to 2 different lines on the left and the right. So you will have at most two horizontal asymptotes. Okay, that's why the highlight is on the word at most. No asymptote, one asymptote, two asymptotes for horizontal, not vertical. Okay, you can have any number of vertical asymptotes because vertical asymptotes comes from the zeros of the denominator. Now, if the denominator has like many different factors, from each factor you get a vertical asymptote, right? Okay. Now let us look at some examples. Again, first a simple example. You have x plus 9 in the denominator here. What's going on? Okay, x plus 9. Why is it not? Okay, you have x plus. Hmm, a second. Okay, I'm not able to write it for some reason. Home, line. Okay. Anyway, from my next video, I'm not going to be using this Microsoft Word document to edit. I thought I'll try with that, but it's got too many problems. No, it's not editing. Okay, let me hope this continues for this video at least. There. So x plus 9. So your vertical asymptote clearly is, sorry, x equals minus 9. And your horizontal asymptote, the numerator, you have not added anything. There's no plus something separately, right? So it is still y equals 0. Okay. Let us look at the second one. X plus 3 times x minus 5 divided by x plus 1 times x minus 4. So your x-intercepts will happen at, now if I want to write as a point, I will write minus 1, 0 and 4, 0, right? You set the denominator to 0 and that is where, oh, sorry, I'm sorry, my bad. I should write on the numerator 0, not denominator. Okay, x-intercepts is when the function becomes 0. So minus 3, 0 and 5, 0. You get the y-intercept when you plug in x equal to 0, right? So if you plug in 0, you get f of 0 equals 3 times minus 5 will be minus 15 divided by 1 times minus 4 is minus 4. So you get 15 divided by 4. That's your y-intercept. As a point, you can say 0, comma 15 divided by 4. Vertical asymptote. Now, vertical asymptote is when the denominator is 0. Okay, so x equals minus 1 and x equals 4. And these factors do not cancel with the numerator, right? So we get asymptote. And horizontal asymptote is, okay, you have not added plus anything, right? Plus 0, you can say nothing has been added separately to the function value. So it is still y equals, oh, no, I'm sorry. I should not say y equal to 0. Um, mm, mm, mm. Okay, here's the thing. What happens in the long run, right? when x goes closer to infinity, what value I will get? We have to look at that for the horizontal asymptote. Previously it was 0. Okay, I'm sorry, I was going by that, like I was simply trying to repeat the same logic. In this case, it is still y equal to 0 because there is no numerator. Okay, so it becomes like 6 divided by infinity, which becomes 0. So your horizontal asymptote was y equals 0. But in the second problem here, when x becomes infinity, you have x in the numerator as well as denominator, right? And I can tell you now, it will be y equals 1. And the reason being coefficients. Okay, if you look at this x, and x, all of them have coefficients 1, right? So as you multiply the numerator, you'll get x square plus something something. Denominator also will give you x square plus minus something something, right? The highest degree terms will be x square in both numerator and denominator, and their coefficients will be 1. So the ratio is 1 divided by 1. Your horizontal asymptote is y equals 1. Okay. Not the shifts, not the plus k logic, from the previous chapter. Okay, I was almost using that. If it is general rational function like this, if the numerator and denominator are both polynomials with some x terms, then you have to see what are their degrees, right? If the degree of the numerator and denominator is same, like x square in this case, then you just have to look at the ratio of their coefficients. Now, how do I know the ratios of the coefficient? Just look at, you don't have to multiply out everything. Just look at the x, like the x terms are the largest degree terms in each factor. If you multiply them out, what do you get as the coefficient? And in this case, it is just 1 and 1. Okay. Now, with this information, can we sketch the graph? Let's see. The x-intercepts are at -3 and 5. The y-intercept is at 0, 15 over 4. 15 over 4 is 3.75. So somewhere here, let's say. And what else? You have vertical asymptote at x equals -1 and 4. So at x equals -1 and x equal to 4, you are going to have vertical asymptote. What else? Horizontal asymptote at y equals 1. Like that, y equals 1. Let me write for the vertical as well. This is x equals -1. This is x equals 4. Okay. Those are the asymptotes. The graph itself will be positive x square divided by x square. Okay. To know the shape of the graph, okay, I have to know whether it is going to positive infinity or negative infinity on any one of the vertical asymptotes. Okay. Now, when x is closer to -1, okay, I'll write that here. X is near -1. This implies the other factor, x minus 4 is less than 0, right? So in that case, when x is near -1, x minus 4 will be negative. So if you are approaching from the right, it will be positive times negative, which will be negative. So it will go towards negative infinity. And if you are approaching from the left, x plus 1 will be negative and x minus 4 is anyway negative. So the negative times negative will be positive. That tells me my graph on the left side is going to look like this. And between, I can now see what is happening. Between -1 and 4, it's going to be like that. And similarly, on the right side here, it's going to be like that. And let me show it more asymptotic to the line y equals 1, like that. Okay. All right. If we are thinking how all these things, pause and think again. I'm just using the facts that I know about the asymptotes. Okay. Eventually, y equal to 1 has to be asymptote. There is only one asymptote, so on both the sides, it has to become closer to y equal to 1. But I have to find out at the vertical asymptotes whether it is going to infinity or minus infinity on each side. That is where I use the logic that when you are closer to -1, x is like -0.99 or -1.001. Then if you subtract -4, it will be definitely negative, right? The whole thing will be negative. Then you have to look at these two factors, the denominator. Okay, let me erase this here and show you. The denominator has x plus 1 and x minus 1, two factors there. Okay, x minus 4 is negative at -1. So the question now depends on x plus 1. Now whether it will be plus infinity or minus infinity depends on x plus 1. And clearly, when your 0 is -1, if you come from the right, x plus 1 will be positive, positive times negative, negative infinity. If you approach that 1 from the left, x plus 1 is negative, sorry, at -1, the value is -1. If you approach that x equals -1 from the left, x plus 1 is negative and x minus 4 is anyway negative. So the product becomes positive and it will go towards plus infinity. Okay. That should explain most of the logic there. Okay. Then you might think, is the horizontal and vertical asymptote is all that we can ever get? And the general answer is no. You can even get oblique asymptote in a special situation. Okay. And that special situation is the numerator is just 1 degree more than the denominator. Okay. Then we get when you divide, you'll get some linear quotient. And that linear quotient means a straight line becomes an asymptote in the long term. Okay. How? Let us look at this example here. You have x square plus 1 divided by x minus 2. So the degree of the numerator is 1 more than the degree of the denominator. That's the main condition. Okay. And you do the synthetic division, you get this 1 comma 2 as your quotient, right? So your function can be now written as, okay, this can be written as the quotient is 1 comma 2, so degree is 1, x plus 2, and the remainder is 5, right? 5 over x minus 2. Okay, and because you have this f of x equals x plus 2, in the long term, when you plug in x equals infinity or minus infinity, this will go to 0 eventually, right? But you are left with x plus 2 then. So that line y equals x plus 2 becomes your asymptote. Okay. And actually, I wrote this extra comment here that sketch the graph. It will be a fun activity to do. Let's do this. Firstly, the asymptote y equals x plus 2. The slope is 1. Um, I'll write that here. Okay, slope is 1 and y-intercept is obviously 2, x plus 2, right? When you plug in x equals 0, you get y equals 2. So your straight line will be, I'm doing a dotted one because this is an asymptote. Okay, that is your oblique asymptote. Let's say this point here is 0, 2. And then what about the graph of the function? And we say that the function is like a hyperbola, 5 over x minus 2. So that is a hyperbola. And where is the vertical asymptote? At x equal to 2, right? If you draw a line here, that will be your vertical asymptote. Okay, when x equals 2. And now think a hyperbola kind of situation, but with that vertical asymptote and that oblique asymptote. And there is no reflection happening here, so the original shape remains. Okay, stretched by a factor of 5, but the same hyperbola. I'll use a different color to now sketch the hyperbola. It will be like this. Getting closer to that line eventually, so that's an asymptote. And when you come closer here, that will be your asymptote. On the other side, this is your asymptote initially, and if you continue there, in the long term, it will be an asymptote on that side. So you basically get, that like narrow hyperbola kind of shape. Okay. All right. Moving on. Now, these are the situations when the numerator and denominator do not have a common factor, right? So wherever the denominator is 0, all of those are, in that case, all of them become asymptotes. Now, we have discussed this right at the beginning, right? You get a hole in the graph if your factor cancels out. Okay. So let us look at an example here. Sometimes the graph of function has a hole in it. Okay. And the reason for having a hole in the graph, the reason for having a hole in the graph is the factor cancels out. And let me write that here. Look at this. And if you factor that x square minus 4 using the a square minus b square formula, right? A plus b, a minus b, that formula. This is x square minus 2 square. So it becomes x plus 2, x minus 2. A square minus b square equals a plus b times a minus b. You must have memorized that by this time. So these factors cancel. You are only left with f of x equals x plus 2. Okay. But unlike the previous case, that at x minus 2, you will not have a vertical asymptote, you will have a hole. Okay. X minus 2 is 0. So you get at x equal to 2, you get the hole. But at what value? See, if you have to sketch a hole, you need to know the value, the y value where you have to sketch the hole. And the hole will be where the value of the function is, f of x, the effective value of f of x is x plus 2. You plug in 2 for x here, you get x equals 4. So, sorry, not f of x equals 4. So that y equal to 4. At that value on y, you have to have a hole. Okay. And so I'm going to sketch a graph for that on the right here. this is x equals 2, and let's say here the point is 2 comma 4, and at that point there will be a hole in the graph. And what about the rest of the graph? The rest of the graph has the equation y f of x equals x plus 2. Okay, f of x equals x plus 2 is the rest of the graph. So that will just be this straight line. On both sides. Okay. Okay. Moving on. Another example with more number of factors. Okay. So to sketch this, first we'll find a hole. And that happens when the factors in the numerator and denominator cancel. So which means you have to write this as in a factored form. X square minus 16 is minus 4 square. So it is x plus 4, x minus 4. And 3 plus x, let me write as x plus 3. Denominator, x plus 3, x minus 3, and x plus 4. Okay. So you factored both numerator and denominator. X square minus 9, which is 3 square, x square minus 3 square became x plus 3, x minus 3. Okay. And if you want to now cancel out the factors, you notice that x plus 4 and x plus 4 will cancel, x plus 3 and x plus 3 will cancel, and you get this rational function x minus 4 over x minus 3. Okay. So what are the values of the denominator which got cancelled? X plus 3 and x plus 4. So f of minus 3 and f of 4 has to be calculated. Because at those points, x plus 3 and x plus 4 cancelled, right? Minus 4, sorry. So f of minus 3 and f of minus 4 has to be evaluated, because at those values, your factors got cancelled out. The denominator was 0. Okay, and it got cancelled. And what do we get? If you plug in minus 3 in the remaining function here, okay, not the original. Oh, okay, actually I should not say f of minus 3, sorry. That's the incorrect way of putting it. I'll just plug in minus 3 in the eventual function. Okay. Let's plug in minus 3 there. I'll just say at minus 3. It will become minus 3 minus 4 is minus 7. And divided by minus 6, which becomes 7 over 6. And at minus 4, it will be minus 8 divided by, I'll just say at minus 4. Minus 8 divided by minus 7. So it becomes 8 divided by 7. Okay. Once again, these values come from here and here. Okay. 7 over 6 and 8 over 7. Where are those values? Let me mark them. At minus 3, 7 over 6 is a little bit more than 1. And at minus 4, again, 8 over 7 is a little more than 1. Somewhere there at minus 3 and minus 4. Okay. And what else we know? Now the only factor that remained is x minus 3 in the denominator. So which means you are going to have a vertical asymptote at x equals 3. And the previous value, sorry, I should have drawn them as a whole and not as a, I think I have 2 minutes, so let me do it quickly. I would have got holes there. Okay. And rest of the graph looks like this hyperbola now. Here's the problem. Okay, now you need to understand this is a hyperbola because this is x minus 3, 1 plus 1 minus, actually, if you do it, 1 minus 1 over x minus 3. That's what you will get if you look at that. Okay. So what's going to happen is, all right, let me write on this side. It will become 1 minus 1 over x minus 3. That will be the graph. Okay. So it is going to be a reflection, with eventually y equals to 1 as your asymptote. Okay. Y equal to 1 will be your horizontal asymptote. You get this by synthetic division. If you're asking, I'm going to circle this here. I should have had more color options. Okay. So I'm going to circle this here and I'm going to just mention that. Okay. If you want, please do the synthetic division and you'll get that. So that tells you that 1 minus something, so y equals 1 is going to be your asymptote. Okay. And that is your asymptote. And vertical asymptote is x equals 3 and with holes at these 2 points. If you notice that these holes are a little bit above the line y equals 1, right? 7 over 6 and 8 over 7, a little bit more than 1. Okay, I'm almost done with my recording, so I'm going to finish this here like that. Sorry, asymptote, and because it's a reflection, it's going to be an asymptote like that there. That will be your graph. So the hyperbola with 2 holes. Okay, I'll see you in the next video. Thank you.